Hello, finishing up chapter 16 of Young and Freedman's University Physics is a optional section, that's the asterisk, on shock waves. So shock waves has to do with situations where the wavelength in front of the source, so you remember the wavelength in front of the source. This is the formula that we had in the previous video. So lambda stands for the wavelength. The wavelength in front of the force is basically the velocity of the sound minus the velocity of the source divided by the frequency at which that sound is being emitted. Now you can see that if the velocity of the source exceeds the velocity of the sound, we have a problem. Then you have a negative wavelength. Basically, this is when you hit the sound barrier. It takes quite a bit of push to push through the sound barrier, and it was only breached by Chuck Yeager at, I think, 1948, first time that a vehicle exceeded the speed of sound. Of course, cracking a whip or a bullet, breaks the sound barrier as well. That's why they make such a loud noise. But so it's called a sonic boom when something breaks the sound barrier. But anyway, so this formula for the wavelength in front of something doesn't work once the velocity of the source exceeds that of the sound itself. In fact, you don't hear anything in front of the source then. If you were within the kind of cone, if you're within the cone, as we'll talk about it in a second, the cone of the shock wave, then you would hear the sound normally. And if you're outside the cone, then you hear the boom, the sonic boom. But basically we're talking about supersonic speed here, where you're exceeding the speed of sound and you're going to get shock waves coming off. Basically, the sound is still being omitted from the front of the aircraft, as it were, but the sound is going to constructively interfere with each other along the line of the sonic boom, as it were, and so that's where the sound is not coming from the engines of the plane or anything like that. It's the sound of the actually exceeding the speed of sound is what causes this. Okay, well, this is a poorly drawn shank diagram. So this is meant to be a plane of some kind, and here is the supposedly straight line behind it. Now, this straight line, the distance behind see, these circles, again, they're poorly drawn, are basically and they should be whole circles. Sorry, they shouldn't be partial circles. They should be whole circles. But what we have is the circle of the sound coming from the front of the plane. These circles are going to constructively interfere along these lines here, and they're going to continue. Of course, this is continuously being emitted from this point, and so the distance of any wave behind the plane is going to be the velocity of the source, times time. That's a simple d equals vt thing. So this, the measure of this line is easy enough. It's simply how fast the plane is going times the amount of time the wave has been moving back in these continuous circles. Now this here is the radius of the circle, and the radius of the circle being omitted is basically going to be the velocity of the sound, because the sound is going to be continuously being emitted in circles. So the velocity of the sound times time, that's where that sound being emitted is going to be at any one point. Well, now we have this angle. The angle between the cone, as it were, three-dimensional cone, can be figured out because we have this right triangle relationship here. This is a 90-degree angle. So the sine of this angle is the opposite over the hypotenuse. And so the sine of this angle is Vt divided by V source t. Now you can see that the t's cancel out. And so what we end up with is that the sine of alpha, this angle between the cone where the sound waves are constructively interfering with each other, the sound boom line, as it were, and whatever the object is, that angle, you just take the arc sine of V over Vs, and you've got that angle. There you have it. Now let's introduce what's called the Mach number. The Mach number is, this is the formula we were just talking about, that the sine of that angle between the cone of the sonic boom and the object itself, the sine of that angle is equal to the velocity of sound divided by the velocity of the source. Well, if you flip this ratio, you have what's called the Mach number, the velocity of the source divided by the velocity of sound. So if the source is moving exactly at the velocity of sound, then you have v over v equals 1. So Mach 1, if something's going Mach 1, it is going the speed of sound. Now, and thus by extension. So if the object is moving at twice the speed of sound, then you have Mach 2 and so forth. Well, there's a little bit on shock waves from the last section, the last optional section of Chapter 16 on sound and hearing in Young and Freedman's University Physics.